All right, hello everybody. Welcome to a C Prime Talk. This is Wes Johnson. He is going to be telling us about some of the fascinating things in the world around us. My name is Tyler. I'm one of the organizers of C Prime. Wes is also one of the helpers out with the C Prime Talks. So if you don't know what C Prime is, we're a student group which is devoted to increasing equity, inclusion, and diversity here on campus, especially in the physics department. One of the ways we do that is through this talk series where we give talks on grad students' research and researchers in general in fields of physics and beyond. And so throughout the talk, we'll have times for questions and discussions amongst ourselves. And if you're here in the room in person, we have oodles of pizza. If you are joining live on YouTube, then we do not have pizza for you, but feel free to type things in the chat. We're happy to answer questions that way as well. All right, without further ado, join me in welcoming Wes.
All righty. So let me just jump in right here. First, I'd like to say kind of motivation for this talk is that, a lot of you have probably seen the simple harmonic oscillator. And here I'll be discussing how it's actually used in research and how you can actually use it to do useful things. It's kind of a small audience, so I actually want you guys to be engaged and just, ask me questions during the talk. I'm going to have some questions for you guys. And yeah, keep it, I guess, kind of informal. Cool. Well, on that note, can anyone tell me who this is? It's a tough one. Yeah, it's a tough one. You can just shout it out. Yeah, bingo. Okay, so cool. Yeah, this is Albert Einstein. Well, why is he in this talk? Well, okay, he's a very important physicist. It turns out he did a lot of important things, and some of those things are going to be relevant for today's discussion. Kind of the first thing is light carries momentum. Okay, so that's kind of an interesting thing. If you know anything about light, it may be, for example, that it's carried by a massless particle. Okay, so how does it carry momentum? That's kind of interesting. He's also known for Brownian motion, which is, I guess, relevant for this talk because it was like the first evidence of atoms, right? So there was this biologist named Brown. He looked at pollen grains and he saw them jiggle, and he wondered, why are they jiggling? And he tried maybe to see if this was something to do with the pollen grains being alive, and he used other specks of rock, and they also jiggle under a microscope. It wasn't until Einstein came along and said, oh, well, this can be explained by atoms slamming in to this little thing and making it jiggle under the microscope. And so that's kind of the first direct evidence that atoms exist. And then he also got his Nobel Prize for this idea that light comes in discrete bits or photons. And so he's kind of the founding father of quantum theory. Okay, so we're going to discuss why there's momentum carried by light. And so there's actually a really simple argument due to Einstein. But what you have here is you have a cart. All right, so imagine this is frictionless, meaning, it just slides along the ground without being stopped. Then there's this, some particles with some energy U. What's going to happen is these particles are going to move to the other side of the cart. That's kind of the setup we're imagining. And so if that happens, we know that energy is related to mass. So U equals mc squared, right? This is like Einstein's big insight. And so if this energy moves to the other side of the cart, then the center of the mass of the cart will apparently change. So that would be kind of bizarre. Just by something moving around inside the cart actually changes its center of mass. Well, the way of getting around this is by seeing that when this energy moves from one side of the cart, there must be momentum imparted on the cart. Okay, and so this clump of stuff carrying this energy U, it could be anything, including light. And since light carries energy, it means that it must also impart a momentum kick on this cart. Okay, and so that's kind of fascinating. Even if you have a massless particle, it can still impart momentum. Okay, have another fun one. Who is this? Does anyone know? Yeah. I heard Feynman. Yeah, cool. Why is he in this talk? Well, Feynman was around in the 80s, and during this time, they were developing some of the first computers. And one of the fun things that a physicist would do with a computer is try and solve physics problems. And for some of these problems, they found that you could find a better technique and solve the problem faster. And for others, they found that there wasn't really a good technique of solving the problem. And so he began to ask the question, well, what are the limitations? What are the fundamental limitations of simulating physics with computers? And it turns out the big insight here is that if you want to simulate quantum physics with a computer, it's actually very difficult unless you have a quantum computer. Okay, so the idea is that, if you have some classical computer, you're limited in a way that you're not limited with a quantum computer. Okay, and so this comes from his famous talk, Simulating Physics with Computers. Can you do it with a new kind of computer, a quantum computer? And this really spawned the research into developing controllable and manipulable quantum systems. Okay, so this is kind of a fun interactive question. There's two parts. How do you factor a number? And then what are the prime factors of 299? And I'll let you guys work on that for a few minutes, and then we'll reconvene. Okay. Well, now you guys have had some time to think about it. Kind of what are your strategies to factor a number into its prime factors? And then also, what are the prime factors of 299? Did anyone get it? It's kind of a hard one. I picked one that was bad.
Is it prime?
It's not prime.
Okay. 13.
It is 13. Yeah, I heard that. Okay.
The other one is.
Yeah, so it's 13 and 23. I kind of was mean. All right, well, basically, your only resort, or maybe the best way of doing it, is to just go through a list of prime numbers and look at their multiplication tables and see if it is one of the numbers, see if it's that number you're trying to factor in that multiplication table. So yeah, basically a simple algorithm that you could do in your head is, divide by 2, divide by 3, divide by 5, and then, as Luke said, if it's not divisible, give up. Kind of the motivation for this question, though, is that quantum computers can factor faster than any known classical computer. That's a very interesting result. It just turns out to be the case that if you have some quantum computer, this black box, that factors numbers, it can do it faster than a classical computer can. Or essentially that corresponding classical algorithm would take much, much longer, especially for a much larger prime number. So that's kind of exciting. It basically means that if you have a quantum computer, you may be able to do something that would otherwise be impossible. Okay, this one's really hard. I'm not expecting anyone to get this one, but does anyone happen to know, maybe, who this man is? It's not Wolverine. The mutton chops threw me off. His first name's Hans. So I'm guessing no one's gonna get it. What's that? No? Okay. His name's Hans Duhamel. Yeah, no one was gonna get this unless you study trapped ions like I do. Okay, so you developed the ion trap. Why do you do that? Well, it turns out that if you want to do very precise experiments, it's nice to have an isolated atomic system. And so essentially what his big contribution was the first geonium atom. And the way you can think about it is like a normal atom. You have a proton, let's say, and then their nucleus, and then some electrons are bound to that nucleus. In this case, you have an electron, but it's bound to the entire Earth by this trap. And that's why it's called geonium. It's kind of an interesting idea, but it allows you to actually control the quantum behavior of the atom. Any questions? Okay, this one's a little bit closer to home. I think someone might get it. David? Yeah, okay. This is David Wineland. Cool. Anyone guess what's right behind him? No, I'm just kidding. Okay. So he received the Nobel Prize for measuring and manipulating quantum systems, right? And he did these experiments right down the road at NIST. NIST is National Institute for Standards and Technology. And so in his Nobel speech, he said, an interesting next step would be to control an ion's motion at the quantum level. The cold trapped ion's motion along any mode axis is harmonic to a very good approximation. All right. And so that kind of motivates me talking about harmonic oscillators to all of you guys. But anyways, if you're not familiar, this is kind of the picture that we're looking at. We have some parabola, and then because of quantum mechanics, this parabola, we don't get any energy level on this parabola. So we get discrete energy levels. And I'll go into more detail of what that means, but basically, somehow this ion trap is essentially this weird looking parabola. All right, now I've kind of discussed a bunch of other people in physics. I'll tell you who I am. Of course, no Nobel Prizes. So my name is Wes, and I grew up in a rural town in Arizona called Cornville. Kind of curious, has anyone heard of it? Probably not. Sedona? Okay, someone's heard of Sedona. Okay, cool. So it's near Sedona. Yeah. So from a young age, I like being outside. I really like math. And I think I would say I like the oscillators. So it's kind of interesting that I came to this field. When I was an undergrad at the University of Arizona, I did an RU. Is anyone familiar with an RU? Do you know what that stands for? Yeah, right. Does anyone have the acronym? Right, okay, cool. Well, yeah, it's a research experience for undergraduates, and essentially what it is allows you to do research as an undergrad over the summer with some physicists, and that's a really nice experience. I definitely recommend it to you all. If you want to talk about that after, just approach me and we can discuss how you apply and all that. I also did a bunch of other research projects that were unrelated to physics. I was in a social insect lab because I thought ants were cool. Ants are cool. And I also studied atmospheric science. But today, I'm a graduate researcher at CU, and I study ion crystals. All right. So we kind of mentioned ion traps. Does anyone have an idea of how you would trap a charged particle? Kind of an open-ended question, but go ahead and talk to your neighbors. All right, so yeah, I mean go ahead.
We were saying you take a sphere, and you have an electric field that's pointed inward in all directions, and you can put something in the center and it'll be repelled by all directions.
This is actually, I think he's kind of leading the question. This is actually a very important point, but this is exciting. Yeah, we're gonna discuss that, but basically, yeah, all I was looking for is electric and magnetic fields. As this gentleman said, one option is magnetic fields, other option is electric fields or some combination of them. It turns out that it's not so simple. This is actually kind of a surprising thing. So what I want you to imagine is you got a bunch of charged particles. You're going to arrange them in some way so that your charged particle in the middle gets stuck and can't go. Because what it means to be trapped is it can't run away forever as bounce around in here. Well, if I have these, then there's always a place where it can pass between them. All right, so that's kind of interesting. Now imagine another scenario. What if I surround this entire thing with charged particles? Right, yeah. Yeah, there's symmetry. Right. There's symmetry. So if you surround this thing with charged particles, then like for example, this field is going to cancel with this field at the location of the charged particle, and so it's not going to feel any force. And so it's like there's no barrier at all. Okay, so it's not so simple. Mathematically, this is related to the fact that you have to solve Laplace's equation. And so a simple argument shows, if I have this potential and I take second derivatives of it, let's say it looks like this, so it's harmonic, basically just meaning quadratic. Then I get this condition: C plus B plus A plus B plus C is equal to 0. And what that means is that at least one of those coefficients has to be negative, right? So you can't trap in all 3 dimensions. Okay, so yeah, static electric or magnetic field can't trap an ion. So notice that it's static and it's also electric or magnetic. And so there's other things you can do. One possibility is you can have a pinning trap, which is an electric field and a magnetic field. And that turns out to work. So you have a static electric field and a static magnetic field. The electric field provides confinement along the axis, and then the magnetic field provides confinement in the radial direction. Kind of the weird thing about this system is that because there's a strong magnetic field, the ions are actually confined by their motion. So right, the magnetic force is velocity dependent. So if you have a bunch of ions in here, they're all going to be spinning around the trap axis. So that's kind of goofy. For that reason, typically in these traps, when you have multiple ions, they have a rotating wall potential. And so basically you have these sinusoidally oscillating electrodes, and that allows you to like fix this rotation frequency of the ion cloud. And so here's a little simulation of what that looks like when you're rotating with the ion cloud. And so you can see the ions settle down and they're basically fixed in this frame, which means, you know, they're stuck to that rotating wall. Okay, so that's one possibility. The other one is a potato chip potential. You might be asking, well, if you have something that looks like a potato chip, how am I going to trap on it, right? It'll trap in one direction because it's confining, but in the other direction, you know, the ball just slides off. And so the secret is it's not static. It turns out that if it's not static, you can actually do this. Okay, and so this is kind of fun. I like showing this because it's interesting. So this is the demonstration. You can't trap with the static electric field, right? In this case, we have a static gravitational potential, but it's not working. Okay, so what are we going to do? Well, it turns out we just spin it around, and this is the magic. This is where the physics comes in. But now watch what happens. It's kind of interesting. As you can see, the ball's not leaving. The ball's kind of trapped. This is essentially how a Paul trap works, is you have an oscillating electric field, and then you have an ion, and the ion, as it's trying to run down that saddle moves, and now it's trapping. And so it gets bounced back. And basically, every time it tries to move, it ends up feeling, on average, this confining potential.
Does it matter what frequency? Like, did this person have to dial in very precisely how quickly the thing is spinning around, or is that right?
It absolutely matters the frequency. I mean, you can imagine if it's very slow, then, you know, the ball will have time to just slide off. So somehow, like, the frequency is related to how quickly it's spinning. But also, if it's very fast, it turns out that you can just eject the ball. Like it starts to move toward down the potential, and then it spins and it gets a kick and it just flies out. Okay. Cool. But it turns out no matter what trap you have, it's basically just a funny looking parabola. All right. And so that's kind of the point of this talk, is I'm going to explain to you how to think like a physicist. And a big part of thinking like a physicist is being able to apply these approximations and study, you know, the complex phenomena, say, of this trap in terms of a simpler idea. So here's a funny quote that I came across while researching this. This comes from Sidney Coleman. He was a graduate student of Murray Gell-Mann. If you're familiar, they worked on QED, quantum electrodynamics. So he knows about oscillators, let's say. The career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction. And I guess that's kind of what we're going to be doing during this talk. All right, so as an introduction, and in case you haven't seen it before, this is our simple harmonic oscillator. And so we can look at it in real space. For example, we have a mass bouncing on a spring, and we just see that it's going to bounce up and down. We can also look at it in phase space, which is going to become important later. But essentially, you plot versus velocity and position. And what you find is that you get this nice little circle. So you can think of this oscillation as, you know, being confined to the circle. This is the frequency of the oscillation, how quickly you go around the circle. And it turns out how big the circle is, the area of the circle is related to the energy. So if I, increase this oscillation, I make this circle bigger, but it still goes around at the same speed. That's an interesting feature of the harmonic oscillator, is that even if it has more energy, it still goes around at the same speed. There's a few other things you can do. You can look at the energy. You'll know, since this system's not interacting with anything, its energy is going to be conserved. And what that means is that even though the potential energy, which is this parabola, even though it's varying during the orbit, the kinetic energy is varying in a corresponding way to ensure that the total energy is conserved. All right, and so that's basically what this is. These turning points are basically at the ends here where it stops. And so you can see that's where the kinetic energy is zero. Makes sense because the thing stops moving. Okay, so kind of my big claim is that every equilibrium is a parabola. That's a big claim, but why would that be the case? I guess just out of curiosity, has anyone here taken Calc 2? Okay, so Taylor series, everyone's familiar with Taylor series? Maybe? Okay, cool. Well, let's say we got some complicated looking potential energy function. It looks like this, okay, kind of nasty. But we know that this is the lowest point. And so if the energy is at its lowest point, then the particle is going to be somewhere, have some energy around here. Well, the interesting thing is, if I zoom in very close to this equilibrium, it's basically just this quadratic. And it turns out that this is always the case, unless you have something very strange that's quartic, or something very strange where it's like a very strong potential, but it doesn't have any lower order terms. It's gonna be quadratic. And so that's one argument that you have for seeing everything as a seeing everything as a harmonic oscillator, is some mechanical system about equilibrium. It's basically going to behave as if it's in a harmonic potential. And so here's a real life example of that in an ion crystal. And so what's plotted is the potential energy as I move along this axis. So here's all of the ions. Here's the ion that we're plotting the potential energy for. So you can see it has this minima right here at equilibrium. The red line is this harmonic approximation. And so you can see this parabola fits very nicely down here. And then, of course, further away, things happen. This is what physicists call nonlinearity. You can see, for example, if you guys are familiar with the Coulomb potential, it goes as 1/r. And so if you get very close to one of these ions, the potential energy just explodes. Okay. Cool. So we're ready for more pizza. If water and ice are made of the same molecules, why are they so different? Go ahead and discuss. All right. Any ideas? Well, I guess, what's like one difference that you just notice, like from touching water and from touching ice? Like how do you feel? Yeah, one is colder, obviously, right? Turns out that this has something to do with the microscopic behavior of the atoms or molecules inside of something. So basically the answer is hot H2O, the molecules aren't very organized and they can move around each other. And, of course, we perceive this as, it's water. So I move my hand through it, whereas ice can't move my hand through it. And why? Because in the cold H2O, molecules are kind of organized together and they're bonded very, well, maybe not very strongly to each other, but they're bonded to each other. So now, it's a solid. Can't just move my hand through. And the only thing that really changed was the temperature. Like it's still made of the same stuff. It's the temperature that changed. Okay, so why am I talking about ice? Well, there's a similar thing going on here that can help us understand ion crystals. And so right here, we have a hot ion crystal, and you can see the ions are jiggling around, right? They're moving away from the equilibrium positions. But as time goes on, these ions eventually settle down to their equilibrium positions. And this corresponds to the energy decreasing. And so we start at 10 millikelvin, which is 1,000th of a degree above absolute zero. 10 times 1,000 above absolute zero. And now we're down to around roughly 2 millikelvin. You can see at this temperature, we're very solid, right? So when we're in this very cooled regime, we're very close to those equilibrium positions, and we can actually use a harmonic approximation.
Sorry, why do these just all flying away from each other?
Oh yeah, right. So yeah, there's two parts, right? The ion crystal is made because we have a trapping potential, and that holds the particles together. But of course, also the particles are going to repel each other because they're all of the same charge, right? And so the question is, why don't they just fly apart? Well, it's because at this equilibrium, the trapping potential is equal in its effect to the repulsive electric potential. All right. So kind of a funny slide, right? This is the ion crystal, and we have the salesman. He's saying we can fit so many oscillators in here. It turns out that these crystals can really be thought of as a collection of oscillators. But what do those oscillators look like? Well, first, what I want to say is that the motion of an ion crystal can be represented as a superposition of these oscillations. So I guess one way to think about this is, imagine you have like a stadium full of people, and they're doing the wave, right? So you see this like ripple going through. You could think about the individual people throwing their arms up, or you could kind of look at like, collectively what's going on. And it turns out that collectively what's going on is usually a more useful picture when you're studying these types of systems. It turns out that if you're looking at the big picture, you can make a lot more progress on your physics problem. Okay, and so for example, in 2 dimensions, imagine we have 2 ions, so they're in a trapping potential, so they're forced next to each other, but they're also repelling each other. What types of motions could you have? It turns out that there are 2 motions in 1 dimension. You could have both ions moving together, and then you could have both ions moving away from each other, kind of like in a breathing pattern.
Is pointing this way, like they're going to the same direction?
Yeah.
It's not like they're going together.
They can go together. So this is oscillating. So the arrows change direction. But yeah, basically like this top mode, ions are going like this.
Yeah.
Bottom mode, they're going like this. And it is anyone familiar? Has anyone taken linear algebra? Cool. Okay, so you probably know about the eigenvalue problem, maybe. Well, it turns out that the equations of motion, these are actually orthogonal eigenvectors. And so basically what it means is that if you diagonalize your equations of motion, you get these two motions. And you can represent any solution to the equations of motion in terms of these. And that's what I mean by superposition. If none of that made sense to you, don't worry. I'm going to have plenty of pictures. You'll still get an idea of what's going on. Here's just a more complicated case. Imagine I have like a plane of ions, in this case, 7 of them. I can still get that center of mass motion where all ions are moving together, but I can get more complicated things. For example, right here, let's see, right here is like a tilt mode, I guess you would say. So the ion crystal is going like this. Right here is a little bit more complicated. It's kind of like a potato chip. Essentially, these ions are going towards you, and these ions are going away from you. And that's what the colors mean. But the interesting thing is, no matter how many ions I have, as long as they're in a crystal, I can essentially understand, and they're cold, I can essentially understand their motion in terms of these distinct oscillations. Okay, and so what does that look like? Well, I'm going to show a simple case for 4 ions. Okay, and so on the left, you're going to see, the ions actually moving around. And this is what it looks like in real space. On the right, you're going to see what it looks like in phase space. And so this is kind of the simplest case. This is the center of mass motion. It basically means that all the ions are moving coherently with each other. And so on the left, you see each ion doing its own little motion about equilibrium. On the right, this is represented by the phase space picture where there's some length representing the energy of that mode, and then there's this frequency about which that mode goes through phase space. Okay, so that's kind of the simplest case. You can obviously have more complicated motions. So here's another eigenmode. And what you can see is the frequency is a little bit higher, so we're going around phase space a little bit faster. And also the ions are moving in a little bit more odd pattern. Like there's still some symmetry to it. For example, it looks like these guys are 90 degrees out of phase, or maybe 180 degrees out of phase. Cool. Well, here's the big claim. I can understand any weird looking oscillation as a superposition of these different modes. And so in the oscillating in the phase space picture, I just see these ions moving around, or yeah, I just see these trajectories moving around in orbit at constant velocity. Okay, and so yeah, I guess kind of compare and contrast. Like on the left, on the right, there's kind of weird looking motions. It's not really clear if there's any pattern, right? The ion's just kind of doing something about equilibrium. But on the right, in phase space, it seems like there's a much clearer pattern when I look at these at the phase space picture. There's these 4 frequencies about which these trajectories move in phase space. Yeah, I guess one thing I wanted to say is that in order to actually see these, I had to blow up the energy of the system. Usually the ions are very close to equilibrium. So you'll notice that, for example, this upper right mode, it's doing something a little bit weird. It's not exactly a circle. The reason for that is what physicists like to call nonlinearity. Basically, it means that, that parabola, if you go far enough, eventually that parabola isn't, next to that potential energy. Your approximation breaks down. That's all that means. Nonetheless, you can still get a useful picture by looking at the phase space. Okay, cool. Now we're ready for more pizza. So how can light change the motion of ions? Cool. Does anyone have any ideas? Bingo. I kind of gave it away at the beginning of the talk, but it is still pretty surprising even to me after, learning. Many hours of physics, many physics lectures. But yeah, light carries momentum. That's kind of the big idea here. We're going to shine light on the ions, and now we're going to be able to kind of control their motion. And so you can see, light has energy. We have made an argument at the beginning of the talk, anything with energy should impart momentum. And then you can see that this energy is related to the wavelength and the frequency of the photon. Cool. So ions can absorb light. And when they absorb light, that's going to change their motion. Okay, and so you kind of have a picture right here. Here's a very simple ion. It only has 2 internal states. It's either absorbed a photon or it hasn't. And of course, in real life, ions are more complicated. They have many electronic states. But in any case, this is the picture we'll start with. So here comes the photon. It's going to excite the ion. Now the ion's in this state, and its momentum's changed by an amount h bar k. K is just it's just the wave vector. It's 1 over the wavelength. It's related 1 over the wavelength. Okay. So that changes the motion. Of course, eventually at some point, and this is kind of the most interesting aspect of this process, if you, I shouldn't say too much here, but I feel like, this is something to think about. I dare one of you to ask your quantum 1 teacher, excuse me, quantum 1 teacher, but if the electronic states are stationary states, why does the atom radiate? And see what they say. It turns out that, at some point you put the ion into the state, it's going to relax to its ground state. And what that means is it's basically going to re-emit that photon, and that also changes the momentum. Okay, and so that's the process. So there are several things that you might want to do. Kind of the first thing is I already told you that we need a crystal. And in order to have a crystal, we need low temperatures. How are we going to make a low temperature crystal? Well, we can actually use light. And so this is the idea behind laser cooling, which of course is very famous and probably one of the things that you'll hear graduate students talking about a lot here at CU Boulder. And so here's a little analogy. I find it pretty accurate because the actual amount of momentum that is imparted by a photon on an ion is very small. But essentially what you're doing is you're shooting ping pong balls at a truck that's hurtling down the freeway. And, you know, if that truck collects enough ping pong balls, eventually it'll come to a stop. Yeah, it's kind of crazy to imagine. For some ballpark numbers, you know, this laser cooling process takes about, you know, 100,000, several 100,000, maybe 1 million photons in order to bring the ion to a stop. Kind of the one detail about this is that after, you know, there's decay, and so after the, you know, ping pong is caught, the ion's basically just going to chuck it in some random direction, and you can't really control that. And so that fundamentally sets a limit to how much cooling you can get, because essentially what's happening here is, you know, you've finally got the truck to come to a stop, and then it's going to throw a ping pong, and then it's going to move a little bit. Cool. So kind of the big picture that I've been describing here is that we have lasers and we have ions. And really, when we put the two together, we have oscillators, which I've discussed already. And then we have two-level systems, which you can think of heads or tails, up and down, or excited and unexcited. And so here's the systems in isolation. I just have an ion that's either in its ground state or excited. And then I have a harmonic trap. I put them together and I get a coupled system. And so now I can imagine transitions where I go from excited or unexcited, but I also change the motion of the ion, which is related to the state that this ion is in the harmonic trap. So basically each of these lines correspond to some number n, and then these two levels correspond to either E or G. And then the coupled system, I have to label each of these states by their corresponding E or G or N. All right, and all that to say that lasers allow us to not just change the internal state of the ion, but also its motional state. Cool, so now we can kind of imagine a more quantum picture of cooling. This is exciting because, of course, you know, this is down the road. We're at GILA, right? We want to do some quantum physics. So you can picture here that I've just got 4 states. So these scribbled lines, these are my states. And they're labeled by, you know, excited, state N for the motional number, ground, state N for the motion number, and N-1. And you can see there's going to be a slight shift due to the change in N here. And that's omega. That's related to the trapping frequency. So it's basically related to that parabola. And then there's going to be this large jump right here, typically large. And that's related to this splitting between my ground state and excited state. So basically how far apart these are in energy. Cool. And so one thing you can do is you can apply a laser at frequency omega A minus omega. And what that does is it basically encourages this transition right here. And so you see I'm going from ground state in motional state to, oh, these are switched. Apologies. So this is N-1, and then this is going to be N. And so we drive this transition right here. Then after some period of time, the ion is basically going to relax. So it goes from its excited state to its ground state. But now I'm at the motional state N-1. Okay. And so basically when you're over here, this is N-1. When you're over here, it's N. And then whether or not you're on the top or bottom, it's E or G. And so, yeah, we first excite here. That changes emotional state, but we're excited. Then we de-excite. This just happens spontaneously. And now you can basically repeat the process. And essentially, you're going to walk down this harmonic oscillator states. So you're gonna go from n to n-1 to n-2, and eventually hit zero. And so for any of you who have taken quantum physics, this is what they call the emotional ground state. It's like this little Gaussian, but that's where the process stops. This is the lowest temperature we can get. This is when quantum mechanically we're in the lowest energy state. Okay. I share this slide because it's cool to know that this was first done right across the road at NIST. And so they actually apply laser cooling. And so you can read right here from the abstract of this paper, with the use of resolved sideband cooling. These are just words. What it means is they're walking down that harmonic oscillator ladder. We can get to the 0 point of motion. That's just the lowest state. 98% of the time. So that basically means 98% of the time you're in the lowest possible energy state, just by using lasers. 92% of the time you can do it in all three dimensions. And basically what that means is for each dimension, you're going to have another harmonic oscillator, and it's going to have another number n corresponding to its motional state. So 92% of the time, I can make all of those n's 0. So that's pretty exciting. This little picture here, this is just comparing cooling, the Doppler cooling with the sideband cooling. The Doppler cooling is kind of like cooling to a higher temperature limit. But the sideband cooling is cooling to a lower temperature limit. All you need to recognize here is that these two curves are not the same. And the reason they're not the same is because this absorption corresponds to the ion going from the excited state to the n-1 state. So essentially, if you're already in 0, there is no -1. So basically, if you're very, very cold in 0, then there's no peak right here. The ion doesn't absorb any light because it can't go any lower. And so yeah, that's all I want to say about that picture. But it's kind of cool to notice that like this is something that was done here in Boulder. This is interesting research. Okay, so I basically described one, how you can cool the ion crystal with lasers, but now I'd like to describe 2, what can you do with it? Now you got a cold ion crystal. What are you gonna do with your cold ion crystal? Well, at the beginning of the talk, as is always the case in a physics lecture, I mentioned Feynman, and Feynman had this great idea that we're going to use quantum computers to solve hard problems. Well, it turns out that the trapped ion system is one such possibility for a quantum computer. And so here's a little schematic. Don't worry what these R's are. I'll describe it in a moment. Here's the C0. Don't worry what that is. It's just some box. But the important thing is we've got ions and we've got lasers coming in here. And what we want to do is we want to take the states of the internal states of these ions, and we want to map them to these states using lasers. So if I'm in my ground state in both ions, I want to go to my ground state. If I'm in my ground excited state, I want to go to my ground excited state. If I'm in my excited and ground state, I want to go to my excited and excited state. Okay, it turns out, and this is not at all clear, I don't expect anyone to understand this, but it turns out that this operation is a fundamental building block of a quantum computer. So if you do this operation enough, you could, for example, make an algorithm that adds and subtracts numbers or factors primes, or does interesting things like that. But it all relies on 2 ions being hit with lasers. Okay, and so here's what the R is. Let's see. Yeah, so the laser pulses perform these operations. First operation is I take my internal state of ion 1, I map it onto my motional state. So if this is the ground state, then this stays 0. If this is excited state, then the motional state becomes 1. So I basically just swap the information. Then the next step is that I do the C0. And the C0 is this controlled NOT gate. Basically what it means is depending on the value of the first thing, so depending on the value of the motion, I'm going to do something to the second ion. Okay, and then at the end, this basically just reverses what we did at the beginning. So we return this motional state back to 0. And so if this was 1, then we map 1 to excited, and this goes back to 0. So basically it's swap, C naught swap. Okay. So if we have enough of these operations, we can create simple logic gates. These simple logic gates are the building blocks of a quantum computer. For context, there's a very similar thing in a classical computer. Each time you fire up your computer in your gaming rig, let's say, to go play Minecraft or something, I don't know. It's actually doing very, very large number of these logic gates. And so fundamentally, you have these states going in, you perform some logic, you have states coming out, but they all are built off of these very, very simple operations. Quantum computers is kind of the same way. So the idea is that if you can do this with a larger number of operations, you can do more complicated things. The other thing I wanted to mention is that this motion is very important because it allows the electronic states of the ion to communicate. So this is basically kind of like our information channel, or like our telephone. It's like how one ion calls up the other ion and tells that ion what's going on. In this algorithm, it's actually very important that this is 0. So it's actually important that we cool this motion to the ground state. This turns out to be very challenging. So with one ion, you can do it 98% of the time in one dimension. At least that's what was done 20 years ago. Maybe it's a lot better now. In 3 dimensions, you can only do it 92% of the time, right? So we'd like to be able to use the motion to make ions communicate, but we don't want to have to like cool the ions down to the absolute coldest possible temperature that we can achieve. And so that's kind of the next step, is figuring out how to make this more robust. That's what a Molmer-Sorensen gate is. And the whole idea is it works with ions in motion. So only reason I show it is because there's a very interesting phase space picture. And it turns out that looking at this as a harmonic oscillator actually makes things a little bit easier to understand. This slide doesn't do that though. This slide is the simple second order perturbation theory. Don't know if anyone's taken quantum 2 or 3, but yeah, you've seen it. All this is to say it's useful, okay? Like if you're learning this, you can go read this paper and you'll actually understand what's going on. You'll understand how to like make ions talk to each other. Okay, so kind of the setup is we have 4 lasers. We're gonna drive transitions. We're gonna play with the lasers detuning from that energy spacing of the internal states. And then with that, the result is we can drive transitions between the states that doesn't depend on n. So you can see here, there's an n right here. There's an n right here, but in this little result, there's no n. And that's good because it means that, essentially whatever's going on with the thermal motion of this ion, these lasers are going to do the same thing to the internal states. Okay, so that's kind of the second order perturbation theory approach. It's not as pretty. Here's the pretty approach. It turns out that you can write the interaction like this. Don't worry, that's not pretty. That's just math. But the important thing here is that we've got these functions A, F, and G. And they actually have a very important interpretation in phase space. So A turns out to be the area in phase space, which is probably why they call it A. F and G are kind of the coordinates in phase space. And so if I want my gate to not be dependent on the motion of the ions, all I've got to do is I got to tune my lasers so that sometime tau, F and G are 0. And what that corresponds to is I go around and I come back to where I started. And at that point, I've now changed the internal states, but I've not done anything with the motional states. It turns out if you have multiple oscillators, you can look at them in phase space, and then the trick becomes, can I modulate my phase and amplitude of my laser beam to make like 100 of these close at the same time? I think right now they have like, maybe 50 is like the largest number of oscillators they have, but essentially you play with your lasers, these all close, and now I don't need to cool my ions all the way down to the absolute lowest temperature. I can just apply this gate and it'll work reliably no matter what motion that state the ions are in. Okay, and this is the last slide. right here, I have a simulation where I've actually reproduced the main result of this paper. But you can see here, something very interesting happens at this at a very special time. So here it's about 1500. Here it's about 250. That's exactly where you return to where you started in phase space. And it turns out if you tune your laser beams correctly, you can actually create interesting states. Unfortunately, there wasn't enough time in this talk to describe everything, but just to give you a little flavor of what's going on here, this is kind of like Schrodinger's cat. Okay, like this is let's say this is alive, and then this is dead and alive. Of course, we can't do that with cats. It turns out we can do that with ions. We can put them into two simultaneous states that are orthogonal, or basically something that's like dead and something that's like alive, something that's very different. Cool, and that's just a demonstration. Yeah, and so the whole point was by looking in phase space and having this phase space picture, we can actually design this interaction with lasers so that we can reliably do things like communicate information between the internal states of the ions, independent of their motion. So kind of the first conclusion of the talk, there's oscillators everywhere. I think this is very, like, I don't know about you guys, but I like to go on walks and think about how many oscillators there are. Maybe it's just me, but let's just take the Earth as an example. The Earth spins. Okay, so there's a day. Earth goes around the sun. There's another oscillator. The Earth actually has an axis, its rotation axis, that is not aligned with its with the plane, and that's what gives us seasons with the plane of orbit. And that also changes over time. That gives us the Milankovitch cycles. Turns out that oscillator has a frequency that is much lower than the frequency relevant for human lifetime, but it controls whether or not there was ice ages. So if you look, you can see that this oscillation lines up very nicely with whether or not there were glaciers stretching down past Canada. And so I just say all this to point out that oscillators are everywhere. They're ubiquitous. Of course, this was an astrophysical example, but you'll find similar examples in your quantum physics textbook as well. Kind of the other point is that light has momentum. We can use light to engineer interactions between ions. So not only can we change the internal state of the ion, but we can also change its motional state. And then the final point is that trapped ions are used for quantum science experiments. So for example, down the street at NIST, they cooled an ion down to its lowest possible temperature. They've also put a bunch of ions into orthogonal states. So you can think of this as like a Schrodinger cat state, where maybe the ions are displaced this way and also this way, and they're in a superposition. Okay, and that is the conclusion of this talk. I hope you all learned something interesting today.
Well, thank you. Yeah, we have maybe time for one or two questions. We do have a QR code or a link if you want to send any feedback. There's a quick survey you can fill out based on that. We have one more CU Prime talk this semester. It'll be in 2 weeks on using Rydberg atoms to simulate the standard model, I think is the title. So that should be fun. And then we'll be done for the semester, but there'll be, I'm sure, plenty of other CU Prime events that you can attend. That's all that I have. So yeah, questions.
Questions?
This is kind of stupid, but if light carries momentum, would you like make a flashlight strong enough to like push them over?
Oh, okay. See, this is we got to think about limits here. If you had an intensity that large, probably you wouldn't be worried about pushing them over. You'd be worried about lighting them on fire.
Okay.
But
if they were,
yeah, but I think what you're asking is actually very interesting. So for example, if you want to Google, there's a NASA proposal to NASA for a little spacecraft to reach the nearest star. If you know anything about space, it's very big. And it turns out that only way to do this that's even remotely possible is to shine a terawatt laser at a little small mirror. Okay, and so photons are going to come in, they're going to go back. It's transferred a momentum 2h bar k. Basically, by shining this laser beam, this insanely powerful laser beam, at a credit card size mirror, we can accelerate that mirror, which hopefully has like, I don't know, a camera or something, so you can take pictures of ET, all the way to the nearest star. Of course, instead of taking like, I think 40,000 years or 80,000, I don't know. Instead of taking tens of thousands of years, it would take like 30. 30 is a nice number because, it could happen in a human's lifetime. Whereas, if you use like some chemical repellent, it couldn't. So to answer your question, yes, you could push something with light. Any other questions? And it can be random. I mean, there's only a few of us. Anything? I could talk about I could talk about my coding issues this morning.
What's your coding issue?
Actually, I don't want to talk about that, but there is something I will mention is that if you're going into physics right now, it's an exciting time because of AI. And AI, is basically going to change the world. I sound kind of like a zealot, but for a concrete example, a few months ago, I used to write code with like, Stack Exchange, which is this website where you go and you look up questions. Now I write code where, I ask ChatGPT a question and it answers it, and like 80% of the time it's right. But the point is that it's still faster. So I would definitely recommend, whatever you're doing now, try and learn some AI. It will probably help you in your future career.